So we will continue with the chair conformation of cyclohexane ring. So before the exam, we have talked about the chair conformations and the chair flip. Okay. So what is important regarding the chair flip or the two chair conformations of cyclohexane ring is that on every carbon in this six-membered ring, we have one axial position, one equatorial position. In the chair flip, the axial position will become equatorial, while the equatorial position will become axial. Okay, so that's what has changed in this process. But what has not changed in this process is that if the bond is going down, it's still going down after the chair flip. If the bond is going up, it's still up after the chair flip. Okay. If we have a substituent attached to the cyclohexane ring, when we do the chair flip, you will see that the two chairs are not exactly the same. In one case, we have the substituent on the axial position. In the other case, the substituent will be on the equatorial position. And we have talked about which one is more stable. Equatorial is always more stable, okay? Because when the substituent is on the axial position, there will be the 1,3 diaxial interaction, which will raise the energy of the whole molecule. All right. So now we're going to take a look at the di-substituted cyclohexane rings when there are two substituents attached to the ring. So there are a couple things that we need to consider when we have two substituents. First is where the substituents are, on which carbon atoms. Second, we have to take a look at which direction that the substituent is pointed to. Okay, so let me use these first examples to illustrate this. So what I have here is a cyclohexane ring with two chlorine atoms as the substituent. These two chlorine atoms are on carbon 1 and carbon 4, and they are both on wedges in this case, okay, which means they both are pointing up, pointing to the same side of the ring. Okay? Now let's take a look at the second molecule. Six-membered ring, two chlorine atoms. One is on carbon 1, the other is on carbon 4. But one chlorine is on the wedge, the other chlorine is on the dash. So these two chlorine atoms, one is up, one is down, they are pointing to the opposite side of the ring. Okay, so let's say if we are going to name these two molecules based on what we have learned, the first one will be named as 1,4-dichlorocyclohexane, right? While the second one, it's still the same, 1,4-dichlorocyclohexane. But from what I just described, you can tell these two molecules are not exactly the same. The chlorine atoms are pointing to different directions, right? So in the first case, when the two substituents are on the same side of the ring, we will call it a cis. And when the two chlorine atoms are pointing to the opposite side of the ring, we will call it trans. Okay? So here we have cis 1,4-dichlorocyclohexane and trans 1,4-dichlorocyclohexane. What is the relationship between these two molecules? They are isomers of each other. Isomers. We talked about isomers before. Isomers have the same molecular formula, but their structures are not the same, right? So previously we talked about the constitutional isomers. They have different connectivity, okay, in constitutional isomers. Now in this example here, the connectivity for the atoms is the same, right? They are 1,4 dichlorocyclohexane. But the chlorine atoms are pointing to the different direction relative to the ring. So they have different spatial arrangement. So this type of isomers is different from the constitutional isomers that we have talked about before. And we call these isomers as stereoisomers. Okay, stereoisomers. They have the same formula, same constitution, or same connectivity, but they differ in the arrangement of the atoms in space. So these stereoisomers deal with the 3D shape of the molecule. Okay, the arrangement of the atoms in space is different in stereoisomers. All right, now let's draw the chair conformation of these compounds. So let's start with cis-1,4 dichlorocyclohexane. Okay, so I'm going to draw one chair, and on carbon 1, I put 1 chlorine going up. Cis-1,4, the other chlorine will be on carbon 4, also going up. So let's go to carbon 4, and on carbon 4 going up is an axial position. So that's one of the chair conformation for cis-1,4. And as you can see here, 1 chlorine is on the equatorial position. The other chlorine is on the axial position. All right, let's do chair flip. After the chair flip, the equatorial chlorine will become axial, and the axial chlorine will become equatorial. Okay, so now we also have 1 axial, 1 equatorial. Right? So for these two chair conformations, if you consider the energy, they should be the same, right? 1 axial chlorine, 1 equatorial chlorine. They have the same energy. Let's move on to trans 1,4 disubstituted cyclohexane ring. So trans means opposite direction. So carbon 1, let's put chlorine up. On carbon 4, trans chlorine will be going down. So at carbon 4, this position going down means equatorial position. So in this case, we have 2 equatorial chlorine atoms, right? Let's do the chair flip. Okay. In the chair flip, the equatorial position will become axial. So carbon 1, we have an axial chlorine going up. On carbon 4, we also have an axial chlorine going down. Now we have 2 axial chlorine atoms. So when we compare the energy, one is 2 equatorial, the other is 2 axial. Of course, the 2 equatorial will have the lower energy, and the 2 axial will have the higher energy. Okay? So Now we have the 4-chair conformation regarding the 1,4 disubstituted cyclohexane. Let's label this 4-chair conformation as A, B, C, and D. Can you give the order of the energy of the molecules from the highest energy to the lowest energy? Just now we've mentioned A and B are equal. C is lower than D. Now you need to compare how about C to A and D to A. So A and B should be in between, right? So energy-wise, we say D has the highest energy. A and B are equal. They are going to follow D because they have only one axiom, while C will have the lowest energy, 2 equatorial positions. Right? So that's about 1,4 disubstituted cyclohexane ring. Moving on, we will take a look at 1,3 disubstituted cyclohexane. So let's see, this is the first molecule, 1,3. So 2 chlorines are on carbon 1 and carbon 3. They are both on wedges in this first molecule. And in my second molecule, still 1,3, but one is on the wedge, the other is on the dash. Okay? So if we are going to name these 2 molecules, we go with 1,3-dichlorocyclohexane for the first one, cis, of course. And for the second one, it will be trans 1,3-dichlorocyclohexane, right? So we have 2 stereoisomers here. All right, let's do the chair conformation. Cis 1,3. So on carbon 1, chlorine is going up. So carbon 1, equatorial chlorine. Carbon 3, since it's cis, so the chlorine should also be going up. And on this position, it's still equatorial. If we do chair flip, the equatorial position will become axial. So now carbon 1, we have an axial chlorine. Carbon 3, we also have an axial chlorine. As a result, in one chair conformation, there are 2 equatorial positions. In the other chair conformation, there are 2 axial chlorine atoms, right? So energy-wise, 2 equatorial have lower energy, 2 axial have higher energy. All right. Next, the trans 1,3. Trans means they are pointing to opposite directions. So if we put carbon 1 chlorine on equatorial position up, on carbon 3, it should be going down. And at carbon 3, going down means axial, right? Now if we do chair flip, equatorial becomes axial. Axial becomes equatorial, right? So in first molecule, we have 1 equatorial, 1 axial. And the second, we have 1 axial, 1 equatorial. Energy-wise, they are the same. Okay? So the conclusion here seems to be the opposite as the 1,4 disubstituted cyclohexane, right? So again, if we label these 4 chair conformations for 1,3 disubstituted cyclohexane, can you give the order of the energy of these four structures? From highest to lowest. Okay, here we go. B, 2 axial, highest. C and D, 1 axial in the middle. A, 2 equatorial, lowest. Right? So lastly, we have the 1,2 disubstituted cyclohexane. So in the first molecule, 2 chlorines are on the wedges. In the second molecule, 1 on wedge, 1 on the dash. So for the name, the first one is cis, 1,2 dichlorocyclohexane. Second one, trans, 1,2 dichlorocyclohexane. All right, now I'm going to leave this to you. Can you draw the chair conformation for cis 1,2? 2 chair conformations. Can you draw the chair conformations for trans 1,2? And then you need to compare which one is stable. Okay, so just as what I did, you are going to get 4 chair conformations, and you are going to list their energy from the highest to lowest. Okay, so try that, and in the class we will go over this. Lastly, what if we have 2 different substituents? In the previous examples, we have the same substituent. So 1 axial, 1 equatorial, it doesn't matter which one. If we have 2 different substituents, like in this case, we have 1,4, but one is methyl, the other is a tert butyl group. And as you can see from the structure, from the shape of the substituent, the tert butyl group will be bigger than a methyl group. Okay? So here we have the cis 1,4 tert butyl methyl cyclohexane. All right, that's 1 chair conformation. Can you draw the other chair conformation after the chair flip? Let's try it. You flip the chair, the axial methyl will become equatorial. The equatorial tert butyl will become axial. But both of these 2 groups are going down. They will still be going down in the other chair conformation. Here we go. Right? So these are the 2 chairs. In both cases, we have 1 axial, 1 equatorial, right? But are these 2 equal in energy, like what we have seen before? No, of course not. The 2 substituents are not the same. As we have mentioned, tert butyl is much bigger, so it doesn't like to be on the axial position. It doesn't like to be on a less stable position. So as a result, we tend to put the bigger substituent on the equatorial position in the chair conformation. Okay, so for these 2 chair conformation, the equilibrium will favor the left one. We want the bigger substituent to be on the equatorial position. Okay?